what's coordinate system, and I will try to make this guy, Nabla, this guy, we construct these relations to make this equation automatically satisfied, okay? So you have to tell me your coordinate system. Over here, I don't need to know your coordinate system. This is coordinate free. The gradient is very well defined in any coordinate system. And it will always make this guy automatically satisfied. Similarly, these together, they result in Nabla squared phi equals 0. Like I said, this is 3-dimensional and 2-dimensional, of course. So this equation is coordinate independent. Coordinate dependent, I'm sorry. Okay. So for VR and V theta, VR is partial psi partial theta, and V theta is negative, there's 1 over R here, negative partial psi partial R. Over there, this is the gradient. Go and look at the definition of the gradient for your coordinate system, you're done. So here, this is coordinate free. The differential geometry people, they like to stress this coordinate free kind of thing, because their whole business is to make things coordinate free. Okay, any question about that? Any question? Please, if you have any questions, stop me. This is like a review. It's not new, right? You should have seen all these things before. We're just making review, but because we will use these over and over again, we need to make sure that we grasp the fundamentals of it. Any question, please? Okay, let's notice the following. So what do we get? So this assumption gives us these two equations, that's fine. What's the first benefit by this assumption? The first benefit is that you got to solve this equation, either this equation or that equation, okay? It just, each one of these incorporates both of the two statements that we have, the assumption and the fact, okay? So just solve this or that. So at the beginning we had the continuity and momentum. And the velocity field, at least, the velocity field, we had 3 unknowns. Now we have only 1 unknown, 5, for example. Okay? So this is one thing. But this is not the most important advantage that we got. Let's see what we got. What are the advantages? First, reduce U with 3 components to only one unknown. Fine. Second, remember, inviscid does not mean irrotation. Right? So Euler's equation, which is du by dt negative nabla b, is rho here. Did I mess that? Rho over there. Rho du by dt, that's correct. Okay. So rho du by dt nabla b, here omega is not 0. For Euler's equation. So Euler's inviscid. Inviscid doesn't mean irrotation. You still have vorticity, okay? And there is something here to stress, that inviscid is a property of the fluid. So like superfluids, they have 0 viscosity. But this guy is a property of the flow, okay? And if you make this, obviously, I cannot make the other way around. I cannot say irrotational imply inviscid. I cannot say that at all. Why? I cannot even dare to say it. Here I can ask the question, but the answer is no. Here I cannot even ask the question why, because this is a property of the flow. If the fluid doesn't have local rotationality, does it make the fluid superfluid? Of course not. I mean, you cannot even ask the question. Does it make the fluid inviscid? This is not. But the effect of viscous stresses are gone. Why? The viscous stresses, do you remember the term of the viscous stresses in Navier-Stokes? Nabla squared U. Okay, this is the viscous stresses. So let's see the Nabla square, which is multiplied by the viscosity. No matter how small or large your viscosity, the Nabla squared U term now, you can write it as Nabla, this is already Nabla dot Nabla U. Okay? Which can be written as by this identity, Nabla acting on the divergence minus the curve of the curve. And you can now see immediately that this guy is what? 0y?
Rotational.
Because of irrotational, because of our assumption. And what about this guy?
0.
0y?
Continuity.
Because of continuity. So for incompressible, irrotational, there are no viscous stresses. Okay? There's no effect of viscous stresses, viscous force. Continuity. So the viscous forces, another viscous stresses, forces, 0. Okay? Within the framework of irrotational incompressible. So this is one of the biggest advantages. You don't need to assume inviscid. No, I mean, it's naturally gone. Okay? This is an important thing. Second, any question? Again, please, if you have any questions, stop me. Yes, David?
So irrotational means that there's no viscous forces.
Yeah.
Okay.
Viscous forces are 0. Okay. Look at this. Look at the relation between phi and epsilon.
And just to clarify it for the
Incompressible.
incompressible.
Incompressible, yes, that's right. Irrotational incompressible. Thank you. Look at the relation between phi and epsilon. So look at this. U is partial phi, partial x. And from an epsilon point of view, this is partial epsilon, partial y, correct? And V is negative, V is partial phi, partial y. The relation between velocity field and phi is very easy. U is in the x direction, it's partial phi, partial x. V is in the y direction, partial phi, partial y. VR in the radial direction, partial phi, partial r. This is very easy. With epsilon, it's the other way around, and you always get the negative sign. This is partial epsilon, partial x. Look at this. Anybody got complex analysis? Anybody remembers if you have two functions that satisfy these two equations? These two equations are very famous in complex analysis and they have a name. Remember?
Something Cauchy equation.
Exactly. Maybe the most famous equation in complex analysis. Cauchy-Riemann equations. If two functions of x and y satisfy Cauchy-Riemann equations, what do you get? Well, we get that the complex function that is composed of these two functions as real and imaginary is, remember what you get out of the theorem? If you have a function f that is function of the complex argument z, z is simply x plus iy, okay?
So it is the complex potential, the F.
Yeah. So, but here I'm talking in general. I didn't specify it. So you have here x and y, and you have z, x plus iy. This is the complex plane, and we have a function of z. This function has a real and imaginary part. The real part is a function of x and y. The imaginary part is a function of x and y. If these two functions satisfy Cauchy-Riemann's equations, then of the theorem, then what? You remember? Then the function is differentiable. Is differentiable. What's so important to prove differentiability in complex analysis? Because in complex analysis, if you have a function simply in real number, function of x, and you differentiate once, it doesn't mean that you can differentiate twice. And if you differentiate twice, it doesn't mean that you can differentiate third. And if you differentiate it, doesn't mean that you can differentiate infinite number of times. And even if you differentiate infinite number of times, it doesn't mean that you can write it as a conversion power series. So this is differentiable, twice differentiable, infinitely differentiable, or analytic that you can write it as a conversion power series, polynomial. Okay. So